Welcome back. Today we covered trigonometric models. Just want to highlight that project number 7 is due today. Project 8 is assigned today. You'll find it on Moodle. That's not due for a good long while, but get started on it as soon as possible. So here at the top of the notes, in this section we discuss modeling other oscillating phenomena. Number 2, sums of sinusoidal functions. Last time we saw that if two sinusoidal functions have the same periods, then their sum is sinusoidal with that period. What if they have different periods? Let's graph y equals sine 2x plus y equals plus sine of 4x. We're going to use something called z-trig. So let's type this into the calculator first. Recognizing that now we're graphing the sum of two sine functions, but the period of this is definitely different than the period of this. So let's type them both in here. Sine of 2x plus sine of 4x. And we're going to use zoom trig. Now, to be honest, I don't know exactly how zoom trig works. I just know that if I have trig functions, sometimes I give it a shot. So we're going to hit zoom 7. And this looks like a pretty good window given what it is. Okay, so apparently that crazy looking function is the sum of these two very well-behaved functions. So we've got a couple of questions to answer here. First one, is this crazy looking function sinusoidal? So is that a yes or a no? Okay, so hopefully we say it's a no because a sinusoidal function is just supposed to go up and down and just be a transformed version of y equals sine x or y equals cosine x. So it's definitely not sinusoidal. Next question, is it periodic? So periodic, remember, just means that it repeats. So does this function repeat? And the answer is, yeah, it does. I don't know exactly, like I haven't seen this exact behavior before, but it sure looks like from here over to here is one copy that we see over and over again. Here to here looks the same as it did here to here. So is it periodic? Yes, it is. What is the period and why? Okay, let's see. So, so it looks like the period is just the difference between this number and this number, whatever that is. Or if you prefer, you can go peak to peak, or you could go, for example, this little peak to this little peak. Any of those is fine. Maybe we can actually look at the equation to figure out what the period is. So let's write the periods of these two things. So the period of this first one, remember the formula for a period is 2 pi over b. 2 pi divided by 2 in this case. So this one repeats every pi. And then the period of this one, 2 pi over 4. So this one repeats every pi over 2. So you've got one function that repeats every pi, another function that repeats every pi over 2. So which one is moving faster? I guess it's this one up here. Every pi over 2, that one repeats. This one is every pi, so it feels like we're going to just repeat every pi, right? Because you'll have two copies of this thing for every one of these, and it seems like the period of the whole thing, the sum, is just going to be pi. So the period of the whole thing is pi, since I don't really know what to write here. You know, since the individual periods are pi over 2 and pi. And I guess I could say they both go into pi, and that's the smallest thing they both go into. Like lowest common multiple maybe is the right phrase. Lowest common multiple of pi over 2 and pi is pi. Okay, so it feels like the period is pi. Is there a way we could get that, get the calculator to confirm that? I think there is. So let's see if we can find the peak to the peak, and let's give that a shot. So I'll do second calc, and then maximum number 4. And then the left bound, so I'll keep it right here. I'm just going to go for that peak that's right up here at the top. So left bound, I'll hit enter there. Right bound, just move it to the right until you are comfortably past the top. Enter, the guess doesn't matter, so hit enter. And so the first peak happens at 0.4696, that number right there. So I want to store that number just so I can use it later. So I'm going to do X out here and hit enter, and it's going to tell me that same number. So we'll store that as A. Okay, let's go back in here. Let's go back into calc, and now we're going to find another peak that's adjacent, so 4 maximum. And then the left bound here, so I said we were going to work on this peak way out here. So you could just repeatedly hit the left arrow. You could also type in a value of X if you happen to know any values of X on the screen, but just have to get to the left of the point you're interested in. Hit enter, move to the right until you get past the point that you're interested in, That's pretty good there. I guess doesn't matter, and we'll get this different number here. So this peak happens at about negative 2.67, so we'll quit out of there, ask it for x right now, and then we'll go ahead and store that thing as b. And then the period should be a minus b, right? It's just the first guy, the bigger guy, minus the littler guy. Oh, look at that, 3.14159 and change. So hopefully that looks familiar. If I just ask the calculator for pi, it's the same up until here. That's just a calculator, like a numerical error type thing. Period is exactly pi, and I think we saw why when we wrote out in red what the periods were. Okay, next question here. What is its maximum value? Okay, this question is actually really hard to answer. Maximum value. So if we just think about the graph of sine, then we know that the maximum value normally is 1. So the maximum value of this piece is 1, and the maximum value of this piece is also 1. So it feels like maybe the maximum value should be 2. All right, well, let's look at the calculator. My window here, the y's are minus 4 to 4 by going by 1s. So let's look at the graph. So does the graph get up to 2? Well, I think this is the second hash mark. There's 3 and 4. 1 is hard to see. So does it get up to 2? It looks like it's close to 2, but gosh, that looks like it's below. Doesn't look like it reaches 2 for some reason. I guess I can type in y equals 2 to really convince myself that it never actually gets there. Yeah, there's a gap in between. So it doesn't get up to 2. Why is that? Well, it is true that the two individual functions, the sine 2x and the sine 4x, both get up to 1, but they don't get up to 1 at the same exact time. So it's not as easy as just adding the one max to the other max, because they don't reach their maxes at the same moment. So when the first function is 1, second function is not 1, it's less than 1. So it doesn't quite get there. So if we want to know what the max is, well, at this moment, our only resort is to just use the maximum function like we did before. So we'll just let the calculator estimate for us what that y value is at the top. So second calc and then max, which is still 4. Left bound, that's fine. And then move to the right. And whatever the y value is, that's going to be our real good estimate for the maximum, about 1.76 there. Okay, so then I guess we can say that the maximum is roughly 1.76, and that's from the calculator. But that is not an easy question. It's not one that that we have the tools to answer this semester. In a calculus class, you will have the tools to figure out exactly why it's up there at 1.76 and change. Okay, 3. Consider two trig functions where one has a period of 4 and the other has a period of 6. What would the period of the sum of these two functions be? So we just answered a similar question here. We had two things where one had a period of pi over 2 and the other was a pi, and altogether the whole thing sum turned out to have a period of pi. So maybe pause the video and see if you can figure out what's going on with these numbers 4 and 6. Okay, so if we're back, hopefully we did something like this. I'm just going to draw a picture, but if we start here at 0, then the first one has a period of 4. So it repeats at 4, and then it's back at 8. 12, we'll do one more for good measure. And then the other function has a period of 6. So I'm going to go ahead and write these numbers on the top. So we'll start that one at 0. The next important number there is 6. The next important number is 12, which is that number. And then the next one is going to be 18, which is out here. So I think we found our winner. These two things will both, if they both start at 0, then they'll both be starting again at 12, which is the first number that they both have in common. So the period of the sum must just be 12. And again, there's a least common multiple thing happening. The lowest common multiple of 4 and 6, that is the smallest number they both go into, is 12. 4, varying amplitude. We can consider functions that are said to have damped oscillation. Y equals AE to the negative KT cosine of BT will oscillate, but with decreasing amplitude. Let's see exactly what's going on with this specific function here. So there's a cosine of 2x, and then in front of it is this 5e to the negative 0.05x. So let's type that into the calculator and use Z standard to see what's going on with this complicated graph. Okay, so zoom 6 is zoom standard. But that looks kind of like a cosine graph, but a little bit strange. The peaks here are not as high each time as they were the previous time, and the same thing with the valleys. Okay, so what's going on there? Oh, all right, so the question says, what's the amplitude function for this cosine graph? And amplitude is in quotes here. All right, well, normally the amplitude for a cosine function would be whatever's in the front. So I guess I'm okay kind of informally calling this the amplitude function. I'll put amplitude in quotes, but the amplitude is this thing in the front, 5e to the negative 0.05x. And we know that that's an exponential decay function, which kind of explains why these the peaks look like they are decaying. And the same thing with the troughs. They're not getting down as far as they used to before. So it says let's graph two other functions on the same window to try to make sense of what's going on exactly here. So I'm going to graph the amplitude function, 5e to the negative 0.05x. And so I'm expecting to see an exponential decay. It's not going to be any old exponential decay. It's the one that perfectly hits those peaks. How come? Well, it's because this exponential decay function is like the amplitude, and the cosine maybe wants to get up there, but it can't. It's capped by this decaying function. So it never gets as high as it did the previous time. It just keeps hitting that thing and then turning around. Any guesses as to what the function is that describes the curve that hits all of these valleys? So hopefully we guess negative 5e to the minus 0.05x. So if we've done that right, then this one should hit all the bottoms, and it does. So that one right there we could think of as having a decreasing amplitude. Okay, let's try another example of an amplitude type function. 5, let's graph these two functions by hand. We'll check our second graph on the calculator. All right, so the first one, y equals cosine of pi over 2x. So that's just an ordinary old cosine function. But what does the pi over 2 affect? So that affects the period. And we know the period is 2 pi divided by whatever b is, 2 pi over 2. Clean that up and we see the period is just 4. Okay, so this is a cosine function with a period of 4. So normally the cosine function starts at the top, up at 0, 1, and this one does as well. And then this guy, instead of repeating every 2 pi, it's going to repeat every 4. And this is kind of convenient because it means that a quarter of the period is just 1. So we're just going to be hitting at these points right here. And then it keeps going down to there and turns around, and then same kind of thing here. We just go every 1 unit over and then connect the dots. Okay, easy enough. So there's our cosine of pi over 2x. But now we've got this x cosine of pi over 2x. So what's a good way to think about this x as it relates to the cosine function we just graphed? We can think of this as being the amplitude. And so we saw before that we graphed the amplitude function up above, the y equals 5e to the minus 0.05x. So it seems like we should graph this amplitude function. So let's graph y equals x. So there's y equals x. And then what's the other thing we should graph? Well, before we graphed y equals negative 5e to the minus 0.05x. So why don't we graph y equals negative x? We can do better than that. Let's try again. So this one, I'll get this out of the way. And then that's still not very good. Swish. Okay, so we've got our two amplitude functions, and we know that cosine is just going to bounce back and forth between these things. So why don't we take a look at where cosine was at its maximum right here at 4. So I'm just going to draw the cosine at its maximum, but instead of a maximum at 1, this one stretches all the way to the amplitude function. And then let's look at the minimum. The minimum right there is at 6, but instead of just being at -1, which is there, the minimum is now way down here. Okay, how about we look at this point right here at 5. 5 was at 0. Well, I'm going to be multiplying 0 by something, but it makes no difference. It's still at 0. All right, let's get rid of some of these that we don't need. At 3, we're at 0, and multiplying 0 by the x in the front makes no difference. What's happening at 2? We're at a minimum. So at 2, we're at a minimum right down there. And then at 1, we're back at 0. That's easy. That stays. And then the next one is what? Okay, this one's kind of a funny one. We should be at a maximum, but the fact is we need to be between the red graph and the green graph, and the red and the green both smushed together at the origin. So even though it's supposed to be a maximum, we have nowhere to go, so we can't go anywhere. So the graph looks something like this on that side. And then on the other side, it's the same idea. There's a little twist here, and it's okay if you don't see this on your own the first time. Let's go ahead and graph the 1, the 3, and the 5, because those are staying at 0, so that's easy. 1, 3, 5. But here's the little twist. So down here, at -2, we should be at our minimum. But the fact is we're multiplying x times whatever the cosine gave you. So we're multiplying x by this -1 right here. But the x in this case is -2. So we're multiplying -2 times -1, and we're getting a +2. So this minimum, instead of being down at -1, is actually up at +2. So it's up there. It's a little twist. It's not that big a deal. Certainly not the most important thing here. That is a maximum, but we're multiplying by -4 in this case, which is going to flip this guy down to -4. So we're going to have a minimum there. The next one will be a maximum up there. Something like that. Okay, and just in case, I want to protect myself a little bit here because this video is public. Technically, I don't think we can just say that the maximum happens at 4. It might happen at like 4.1 or 3.9. There's calculus work to be done to determine exactly where that maximum happens, but it's close enough to 4 for our purposes that I'm content to just say draw it up there at 4. So let's check this graph on the graphing calculator. So clearing all this stuff, and we'll type in our new function, which is just x cosine of pi over 2x. Oops. X cosine of pi over 2x. So we're going to graph that, and then we're also going to graph x and -x. And so we see our decreasing amplitude thing here in the middle, and then it's going to get stronger as it bounces around out there to the right. There's your red line, the y equals x, and then the green line is that. So this looks quite good. And like I said, the maximum is actually not technically exactly at 4, but it's very close to 4. And it's hard to tell looking at the picture that it's not perfectly 4. So close enough. All right, next page. 6, varying midline. What happens if we add a varying quantity? Before we use the calculator, draw your best guess for the graph of y equals x plus sine x. Pause the video, give it a shot. Okay, so what I'm going to do first is just graph y equals x. So that'll be our regular line going right through the origin. And then we're going to think about sine x, but instead of sine of x bouncing up and down on the x-axis like it normally does, it's now getting pushed up by whatever that red thing is. So the sine function is going to grow, and it's going to go up and down and up and down and up and down. And then down here, the sine function will be way negative, and we'll get stuff like that. So it's going to look something like the green. And let's type this thing into the calculator here. So I like graphing y equals x. You know what, let's not graph that first. Let's just graph x plus sine x. And before I hit enter here, again, I just want to say that I think this is a perfectly good first guess, this green thing that we've drawn. Technically, when we look at the more precise graph on the calculator, we're actually not going to see the function decreasing. Okay, it's not decreasing for long in this picture, but technically it actually doesn't decrease at all when we look at it. Again, there's calculus reasons for why that's so, but I think at this stage, this green curve is a very good guess for what this graph is going to look like. So here's what I was talking about. See how it's flat there instead of decreasing like I drew it, so it was decreasing. But it turns out it's just flat. It never actually decreases. If we graph y equals x, we'll see that just kind of going through the middle, if that's an okay word to use here. And then you could also graph sine of x if you really want to clutter up your picture. And so there's, relationships here. The sine function is increasing really quickly in here. This crazy curve thing is increasing really quickly in the same space. The sine function levels off. This guy also levels off. Next, the sine function would decrease. Okay, so this guy never technically decreases, but details. Okay, number 7. We now talk about a musical phenomenon known as acoustic beats. Suppose the note of middle C resonates at a frequency of 256 hertz, which is periods per second or cycles per second. That's a lot of sine oscillations per second, but that's what it sounds like when you play middle C. It's 256 complete sine oscillations per second. We can model the intensity of a perfectly tuned C by this formula. I perfect is equal to cosine of 2 pi times 256t. Don't worry about the details here, but I will say there's a project coming up where you're going to look quite carefully at the relationship between sound and frequencies, and then the corresponding function. I think we might use sine in the project, but cosine is the same. Okay, so that guy right there has a frequency of 256. You can check. What can we check here? If you take 2 pi and divide it by this thing, you get 1 over 256, which means that the period is 1/256th of a second. So how many complete cycles would you get in a full second? You get 256 of them. Okay, we haven't really talked much about frequency, and I don't intend to here. So if you missed that, that's okay. A sharp C, one that's slightly out of tune and high, might have a frequency of 262 hertz, a little bit bigger than this guy right here. So let's fill in the formula for the intensity, or just the formula for the sharp note. So apparently it's cosine of 2 pi times, and then right here we just put the frequency, 262 in this case, and then the T. So what happens when we add the intensities? That is to say, if you were to play on one piano a perfectly tuned C note at 256, and then on another piano a C that's just a little bit sharp, a little bit higher than what it should be, and we want to listen to these things together, what are we going to hear? Okay, so what I'm really asking you to do is add this function, and then we'll analyze the result. Turns out you need an identity from your book that we're not going to be proving, but you can take a look. You can look it up in your book. It says if you want to add cosine of something plus cosine of something else, which is exactly what we have, right? Cosine of something plus cosine of something else, then you use this formula right here. So you should verify what we're about to look at down here. Like pause the video and actually plug in, there's your U and there's your V. Plug them into this and make sure you agree with what I've written up here. But we should get 2 cosine of 2 pi times 3t times cosine of 2 pi times 259t. Okay, so 2 cosines multiplied together. I'm going to focus first on this cosine right here, and I'm going to say this cosine is rapidly moving up and down, like really, really quick, 259 complete cycles every second. This guy I'm going to think of as being my amplitude. So the amplitude is going to be changing. But this amplitude is has a period of 3. So this guy is going to cycle up and down every 3 seconds, once every 3 seconds. So if I'm out here at 3 seconds, it goes down, comes up. It's a very slowly oscillating amplitude compared to the frenzy of the purple thing. Okay, thus we have a slowly changing amplitude. That's the red thing. Those are the beats. And a pitch that sounds like 259 hertz. That's this guy right here, which is a little bit higher than C. So I don't know how this is going to come across in the video, but we're going to give it our best shot. We're going to check out this GSP file that I made, and then we'll take a look at some graphs. Okay, so I've got here T1, which is the 256 hertz, and you can see the first function that we're graphing, or that we're going to listen to, is cosine of 2 pi times T1, 256 times x. So that right there is just this formula right here, cosine of 2 pi times 256t. So let's come back here. So on Sketchpad version 5, there's the ability to just listen to sine or cosine function. So again, I don't know how this is going to sound. I'm going to hold my little microphone up to the external speakers here. I might not need to do that, but I'm hoping that some of this comes across in the video. So we're going to first listen to middle C. Okay, so hopefully that came across. It wasn't too annoying. If it was annoying, I got bad news because it's going to get way more annoying as we do this. Okay, next thing I'm doing is I am going to graph or listen to cosine of 2 pi times T1, the same 256, plus 10 times the length of this line segment. And I can make this line segment shorter or longer. And so at the moment, the line segment is 11.51, so I multiply that by 10 and I get 115-ish. So it's just going to be adding 115 to that number. So whatever that puts us at, 371. So what we'd be listening to is not a note anywhere near that middle C. Where's our thing? It's here. So I'm not showing you 262 initially. I'm showing you something that's way off the charts at like 371. So let's listen to that one. It's going to be quite a bit higher than the first one that we listened to. So here it is. Okay, so we've got those two of them together. Again, one more time, I don't know if we can hear it from far away, but middle C and then middle C plus. And as I make this thing smaller, you're going to hear this plus get lower. And it's getting closer and closer to middle C. So here's the altered middle C, and then here's middle C. So they're not too far apart from each other. So here's where the funny business happens. I'm going to listen to them both at the same time, and I promise you, I hope this comes across okay in terms of the sound in this video, but I promise you I'm not doing anything funny here. I'm just going to listen to one note, and then the second note, but we're going to listen to them at the same time, and we're going to hear something that is maybe quite surprising, unless you've got a musical background. So here we go, and we're going to then change the length of this thing right in here. So that right there that we heard were the beats. We heard a slowly oscillating amplitude. That was this thing right here in the front. And then this really wild oscillation, which sounded an awful lot like middle C. Turned out it was going to be something a little higher than middle C. But again, there was no funny business there. And if you have any practice like tuning a guitar, sometimes people use this idea of beats to try to get a guitar in tune with itself. I don't know if they do the same thing with pianos, but I guess you could. Although maybe you couldn't. No, I think it's not working with pianos. So if that came across in the video, then super. If it didn't, I do think it's a demonstration that's worth seeing and hearing. So certainly you can come find me in my office and I can show this to you if it didn't come across in the video. Okay, so one other thing I wanted to look at was this GeoGebra file. So let's open that. Okay, so here is a graph of cosine of 2 pi times 256x. That's our middle C in tune. And the other one is a cosine of 2 pi times 356x, which is a note that's quite a bit of a higher frequency. And they're added together. So I'm not showing you these two graphs right here, but you add those two graphs together and you see this. And what we're going to do is we're going to change this 100. Right now the 100 is the difference between the 256 and 356. So we're going to make that 100 smaller, and this 356 is going to get closer and closer to the 256. And we're going to watch what happens to the graph. So we'll move it smaller here. And we get these kind of crazy patterns. It's not really clear that it's repeating yet. You can see the peaks are getting smaller, and so I don't see a full cycle of this crazy graph yet. But we'll keep moving to the left. And now it starts to feel like we are looking at complete cycles. So it looks like this is a complete cycle right in here. Is that true? Well, maybe not quite. I'm looking at this kind of funny up-down business, and I see it looks like it's repeated. No, that's not quite right, because the first one was taller and the second one was shorter. So it looks like we're kind of getting in there. Maybe this is the one that's repeated, but we're going to keep kind of making these two notes closer and closer together. And eventually we get something where we say, okay, this is what we were listening to right here. So you've got your note of frequency like 259, and it goes up and down at a frequency of 259, but then the amplitude is changing based on this varying amplitude function here, which is a pretty slowly changing amplitude function. And literally what you hear is the sound being very quiet right there, and then getting louder, 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 and then getting quieter and quieter until it's kind of blinks out of existence. And so that's one beat that you would hear. Now it might happen so fast that, I mean, it happens way quicker than I'm talking here, but you'd hear it get loud and then soft and then just kind of vanish for just a moment, loud and then soft and then vanish. And as we make these two notes closer and closer to each other, you can see that the length of time between, let's move it this way, between one vanish and the next is getting bigger. And that's what we heard when we listened to the sketchpad thing, was that the oscillations, the beats were happening, they were taking longer to happen, and it felt like they were kind of going more slowly. And that's exactly what happens when you make these two notes very close to each other. Okay, so again, there'll be a project that you will play around with to get some more experience with that, but I just wanted to show you and have you listen to some of that sketchpad stuff. Activity is on the next page. I'll make a video for it, but again, give it a good shot on your own before you look for the video.